3.5. Mathematical modeling variation. Now, we've done modeling and things like this before. A lot of times when we say the line of best fit or the equation of the trend line. So just a little review of how we've done that on our calculator. Now, typically we don't type in zeros, but we find a 0 year. So let's say that our 0 year is going to be 2000, only because the fact that since it's already in the year, it's going to be easier to do that. So typically we've gone to stat, we've gone to edit. If anything was in our calculator, we cleared it out. We did not delete, we cleared it out. We type in our X values. Again, I have a 0 year at 2000, so I'm going to type in 3 all the way to 10. And then I arrow over and I type in my Y values. This is my input, the year, and this is my output, the Y. And then we would go back to our stat and we would calculate. We would calculate our linear regression model, okay? The equation of the trend line. So if I asked for the equation of the trend line and I asked you to find it on your calculator, we'd have our Y equals 0.8952x, and using this because it's a linear model, and then because this is positive, that's why this is a plus, 38.355, and actually that would round this up to 6 because that 5 rounds up to 9, so this becomes a 6 at 0. Now, the closer that this r squared or the r is to 1, that means all of these data points are very, very close together. That means within our Medicare enrollment, E is for a larger number, it's saying that it's a pretty linear model. It's like a direct linear model, bringing us to this, a direct variation. Now, sometimes we can always do that, and the closer it is to 1, the closer it is going to say it's going to be a direct model. If you have a direct variation, that means y varies directly as x. So the change of x is directly the change of x will be directly proportional to y, which is what I said for number 2. And this is for some non-zero. So in this case, we had this 0.8952. We're always typically going to have some sort of non-zero constant. K is a constant of the variation because the x changes with the y. So if we look at this problem right here, it says the income tax. So I'm going to put this says T. The income tax is directly proportional to the gross income. I'm going to say this is my G. Okay. You are working in Pennsylvania and you state income deduction is this for your gross monthly income. So this is telling you that T is here and G is here. However, I want to set up a mathematical model. So when I'm doing this, I'm always looking back to this. It's directly proportional. So if I want to have this, it says T is directly proportional to G. So this is kind of where we're starting from. We know that T is proportional to G, but we have to figure out our constant K. So we have this T, this 46.05 is equal to our K, and our G here is 1,500. So if I divide that over, I get 0.0307 is equal to my K. So my actual model looks like this because now I found out what my K is. It says my gross income is proportional to the taxes that I have. I want you to pause the video and try to example 3 by yourself. And I is directly proportional to P, so it looks something like this. So I can write out, because of the fact that my I is equal to 187.50, my P is equal to 2,500 to figure out my K, and this is what my model looks like. So now I have direct variation with the nth power. So this is like the same thing. The only difference is that my x might have an n power to it. So if I'm looking at this equation, or pause the video and read that for me. So right here it says it's directly proportional. So the distance is directly proportional. So we're going to have k times something to the square of the time it rolls. So t squared. So it's telling us that t is equal to 1 and d is equal to 8, so that we can figure out what our constant k is. So pause the video, find the constant k. Your constant k should have been 8. So if I write this, this is my model that I'm looking at. So it's saying how far will the ball travel during the first 3 seconds. So the distance, when I have 8, and then I have my t squared. So if I put that in my calculator, which we actually don't need our calculator, we could actually just solve this. This would be 72. In this case, it's always going to be feet. Try to do question 5 by yourself. So this is what we have, our t squared times k. If we found our constant, we should have gotten 16. Now it's asking for 6 seconds. If we plug in 6 seconds into that, we would get 576 feet. So that's direct variation. Then we have inverse variation. Inverse variations and when it's inversely. So basically kind of like the opposite, but it's the same idea. Except when we have an inverse variation, we're dividing by our whatever is inverse directly. So if I'm looking at this, it found that the company, actually pause the video and read this yourself. So it says the demand varies inversely to the price. So when I'm looking at this, the demand varies inversely to the price. So I still have a constant K, but depending on what the price is, this is what it kind of looks like. It says if the price is $6.25, the demand is 400 units. So again, we still need to find our constant K. So in this case, our constant K is 2,500. So it's saying this is what our inverse looks like. Saying what is the demand if the price is $5.75? Find that for me now. Should have got roughly 434 units. Why did I round down? Why did I not do 235? Because when you're talking about actual demand, when you're talking about an actual thing, we are going to always round down in this scenario. If you rounded to 435, I'd actually still count it. So I'd like you to try to do this next one by yourself. You should have gotten the inverse variation as 1,650 divided by P is equal to my demand. If it was $3.25, it would be roughly about 507 units. So right now, that's it. We're going to do the rest of this in class together. So have a wonderful day.